Hello! Thanks for joining me. We're about to go through and do some practice problems. Now, you know, we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin. Let v be the vector 4, minus 3, 5, u, the vector 4a1. We're asked, find the value of a so that the projection, and here, let's make sure we understand our notation. We're projecting u onto v. So see how that v is small there? We're projecting onto v. And what is that projection? It's 6/5, negative 9/10, 3/2. All right, so what do we have? Well, we have our projection. And so we're sort of trying to figure out what's the right vector that made all of this true. So let's start by saying, hey, you know what? There's actually a formula for projection. So that's probably a good place to start. So if we're going to project the vector u onto the vector v, then what we would have is you take the dot product of u and v, divided by the dot product of v and v, and this is a number, and this number you scale the vector v by. Okay, so that's how you find the projection of a vector onto another vector. Now, what do we know? Well, we know these v's, and so we just sort of have to recover what this value is. So let's think about what's going on here. So in particular, remember that when we talk about a projection onto a vector, it's a multiple of the vector that we started with. So we say, how can I scale this original vector v to get that vector v? Or if you like, how do I get back? And well, we can think about things, and you say, oh, you know, pick an entry. Any entry will work, right? Yeah. Well, let's say, suppose I pick this entry 6/5. What would I have to multiply 4 by to get 6/5? Right? So 4 times what equals 6/5? That's my question I'm asking right now. Well, we can think about that. We can divide. We say, well, that says what we're scaling by is 6/20 or 3/10. So I claim, and let's verify this, that if you take 3/10 times this 4 minus 3/5, then that's equal to 6/5, negative 9/10, and 3/2. Well, let's check this just to make sure we're feeling good about this. Okay, so 3/10 times 4, well, it better give us 6/5. That's what we came up with. And it does. It's 12/10. It's just 6/5. 3/10 times negative 3 is negative 9/10. And then 3/10 times 5, well, the 5 into 10 makes 2, so that's 3/2. Okay, cool. Now, why do all this? Well, what just happened here? We say, hey, you know what? Here's this v. So this tells us that 3/10 is u dot v over v dot v. Like, oh, well, that probably is useful information. And it is useful information. Okay, so now let's update what we know. We know that u dot v over v dot v is equal to 3/10. But here's even better news. These are all numbers now, right? Not vectors. We can actually compute u dot v. So we take the dot product, and so that's going to be the dot product of, let me get that right there, 4a1, that's u, 4 minus 3, 5, that's v, and it really doesn't matter which way you do it in, but make sure you get the downstairs right. You want to make sure you pick the right one, so it's v. So it's v dot v. So it's 4, negative 3, 5, and 4, negative 3, 5. Okay, so that would be 4 times 4, 16. And then minus 3a. And then plus 5. Downstairs, we'd have 16 plus 9, because square of negative 3 is positive 9, plus 25. All right, that's 21 minus 3a. Downstairs is 50. Okay, so we're getting closer, almost there. 21 minus 3a divided by 50 is the same as 3 over 10. Well, let's move that 50 across. 21 minus 3a, well, that's 3 over 10 times 50, and 10 goes into 50, which leaves us with 3 times 5, which is 15. We can move things around. 21, subtract 15 is 6. Move the 3a across. 6 has to equal 3a. And so, our conclusion is a is 2. And we're done. That's it. That's it. So what did we do here? Well, what we did is we said, hey, we know how projection works. We know what the formula is. And so we used that to figure out what this u dot v over v dot b is. And then once we had that, it's just a matter of saying, okay, what is that force about A? And all right, woohoo, nice, nice, progress. Find two integer values of c so that the vector 2 minus c, 2c squared plus 3 minus 5, is perpendicular to the vector c plus 1, 1, 5. All right, now there's a really good key word here. Perpendicular. Now, what does it mean to be perpendicular? It means that you're forming a right angle, right? They're coming in at a 90-degree angle. So we say, okay, great. So we just want to make sure we have a right angle. Well, how does one check if something is at a right angle? Well, for vectors, there's a really easy check. That check is if the dot product is 0. So we say, oh, great. And dot products are pretty easy to compute. So we have an idea. We're going to take 0, and we're going to set that equal to the dot product. So 2 minus c, comma, 2c squared plus 3, comma, negative 5, dot that with c plus 1, 1, 5. All right, let's go ahead and carry out this dot product. So we have our first terms, which are 2 minus c times c plus 1. Then we're going to add, not comma, add, right? Because dot products, you multiply, 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 but then you add the results. So add 2c squared plus 3 times 1. And then add negative 5 times 5. Okay, well, let's expand. So here we'll do some foiling. What do we have? Well, we'll get 2c plus 2, and then we'll get minus c squared and minus c. Here we'll get a plus 2c squared plus 3, and here we'll get minus 25. Okay, so we've multiplied, we've expanded, now we're going to collapse, and by that I mean we're going to gather. So let's see, we have powers of c. Highest are the squares. We have a 2c squared subtract c squared, so that gives us c squared. All right, good. Let's just keep track of what we've gathered. So we got the c squared, it's taken care of. Next up, let's talk about our c's. As they say, oh, say, can you see? Well, there's a 2c, and there's a minus c, and that's it. All right, 2c minus c is a positive c. You say, okay, anything else? Well, we've got our constant terms. All right, well, what do we have? We have a plus 2, a plus 3, minus 25. So 2 plus 3 is 5. Subtract 25, we get minus 20. All right, now, we're in great shape. We've reduced the problem to saying, oh, we need c squared plus c minus 20 to be 0. We like things equal 0. So now we say, oh, if you just factor, get the roots, life is good. Yes, life is good. So let's think about this. Now, we do think it's going to factor. Why? Well, because they kind of gave it away. You see how they said find two integer values? That tells us it better factor. So if it doesn't factor, mistakes were made. All right, so putting on our factoring hat, we say, all right, we need two numbers such that they'd multiply together to give us negative 20, but would add together to give us positive 1. Well, 20, that's like 5 times 4, so let's see. Plus 5 and minus 4, I think that'll do it. So let's check. So I claim c plus 5, c minus 4. Now, always good to double check, right? C squared, that's good. Minus 4c plus 5c. Oh, nice, plus c. Cool, cool, cool. And minus 20. And of course, because this equals 0, we say, well, when does each part equal 0? C plus 5 being 0 gives us c is negative 5. C minus 4 equals 0 gives us c equals 4. And so our two answers are negative 5 and positive 4. And then we're done. Great. So remember, when you see the word perpendicular, there's going to be two ways you're going to see it. There's check if two things are perpendicular. Dot. Make something perpendicular. Cross. So here we were checking. So that's why we're going to do a dot product. I suspect there will be other problems where we want to create a perpendicular. That's when we're going to pull out our cross product. But of course, that's a different problem. Maybe we should look at some of those, eh? All right. Find the area of the triangle having vertices P321, Q455, and R235. Now this just means there's a point we're calling P and the coordinates are at 321. There's a point we call it Q, coordinates are at 455, and so forth. And simplify your answer. Okay, cool. Now when you see things like simplify your answer, we should hope it simplifies. Basically, try to get as much down as you can. If there's a square root involved, spoiler alert, there may be square roots involved when you find areas of triangles. Look for squares inside them. But let's see what's going on. Now, there's a clue on what to do on this. Because we say, well, we have a fairly limited tool set. And we say, okay, what's our clue? We say, oh, area of a triangle. Now, the clue is to say that we actually have tools to find area. There's one tool in particular that we've talked about, and that's cross product. So just to recall, I can spell that. If I have a parallelogram, so I have two vectors u and v, and then I can just move v and u to match, so I have this whole thing. The area is the magnitude of u cross v. And let's go ahead and put little vectors on top. There we go. Now that's for a parallelogram. Well, how does one go from a parallelogram to a triangle? We pull out our scissors, right? So we're going to cut our parallelogram in half. We say, that area is, well, it's half of u cross v. So now we're like, oh, okay, cool. So we have a plan. We just take our two sides, the vectors for the two sides, take the cross product, take the magnitude, multiply by half, life is good, and we're great. Now you might say, hey, well, this is easy. We've got our vectors, right? There's a vector, there's a vector. We're all good, right? Right? No, we are not all good. Now, our problem is these are not vectors. P, Q, R, they're not. They're points. Points are not vectors. Now, there's relationships, and we can use those relationships to move from one to the other, but we have to be careful here. So, the good news is we don't have to be super precise. We just need enough to get our intuition going. So let's suppose we mark our points. And when I'm saying we don't have to be super precise, what I'm really saying is that when we draw here, we're going to just sort of put 3 dots. Say, well, okay, here's P, which is at 3, 2, 1. Here's Q, which is at 4, 5, 5. Here's R, which is at 2, 3, 5. And we have our triangle that goes between these points. And if we wanted to, we could even be fancy. We can shade it in. We don't need to be shaded in. Again, it's not actually important that you get these points precisely plotted. We just need to get intuition. Now, what do we need? We need vectors that represent the lengths of these sides. And you might say, well, which sides? There's 3 sides. You only need 2 sides. And here's what I recommend. Pick a vertex. Any vertex works. Now, I'm going to be biased and I'm going to pick P. There's no reason to do that other than it was the first one. So I'm going to anchor myself here. And now I'm going to create a pair of vectors that goes from P out to my other vertices. Now the way we find vectors is we remember what vectors are. Vectors represent change. So I say, okay, if I start at 3, 2, 1 and I end at 4, 5, 5, what was my change? And you do it entry by entry. So I went from 3 to 4, that was a change of 1. 2 to 5, that's a change of 3. 1 to 5 is a change of 4. And when I say a change of 4, they're positive. They don't always have to be positive. For example, here, P to R. I went 3 to 2, so that says, oh, down 1. 2 to 3, up 1. 1 to 5, up by 4. So these are my vectors U and V. And so now we are ready to take their cross products. Okay, so important thing, 1 is you have to know what tool to use. 2, make sure you've got the vectors. It's very tempting to be like, aha, vector 3, 2, 1, 4, 5, 5. No, 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 no. No, 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 no. Don't do that. All right, okay, cool. So here we go. We have, and you might say, which order do we do it in? The answer is, it doesn't matter. It won't matter. If you change the order, you'll only change the sign, and then when you take the magnitude, it won't matter. You might say, well, wait, you chose P. What if I'd chosen Q and chosen those vectors? You'd get the same answer. You might do a slightly different computation, but you get the same answer. So just pick one vertex and go with whichever vectors you get. So 1, 3, 4, cross, -1, 1, 4. And you might say, well, which vertex do I pick to make it work the easiest? And I'll tell you, there's no real way to know. So just pick and move ahead. Okay, so I do cross product by matrices. I put in my ijk, and I put in my entries in the first one, 1, 3, 4. Then put in the entries in the second one, -1, 1, 4. Okay, so remember, we're going to do diagonals here. So I'm going to grab a color. So when I talk about diagonals, we've got the 1, 3, 4. That's going to be 12i. J times 4 times -1. That's -4j. Then k times 1 times 1. That's plus k. So you've got sort of the down diagonals. And remember that when we hit the edge, wrap around. So it's k, wrap around 1, 1. That's only half the story. Now we have to do the up diagonals. Okay, so we have this up diagonal. So -1, 3k, that's -3k, but we subtract. So we're going to subtract -3k. Then we have 1, 4, wrap around I. That's 4i, but again, subtract 4i. And then finally we have 4 times 1 times j. That's 4j, but we subtract 4j. Okay, so let's see. What do we have here? 12i subtract 4i leaves us with 8i. I'll write that as an 8. Minus 4 subtract 4. That's a minus 8. And then I have 1 and subtract minus 3. It's 1 plus 4. Sorry, 1 plus 3, which is 4. 8 minus 8, 4. Okay, now that's our cross product. Next thing is we're going to find the magnitude. Okay, so here we go. How does one find the magnitude? Well, I'm going to do it in two ways, and then I'll talk about the ideas. So the first way is just like, okay, I'm finding the magnitude, and so I take the square root of the first term squared, which is 64, plus the next term squared, which is 64, plus the next term, which is 16. And I say, okay, 64 plus 64 is 128. Add 16, that's 144. So that's the square root of 144. And what's the square root of 144? 12. Cool. That was actually kind of nice. They gave us a really nice area. All right, now I want to do a second way. Now, sometimes you're going to get numbers here and like, oh, you're going to have lots of big numbers here, and it's like, ah. But notice something about this vector, 8 minus 8, 4. Those numbers have something in common. They all have a factor of 4. So this is the same as, let's pull out that common factor and move it out to the front. So I'm going to pull out a 4, and then I'm going to have 2 minus 2, 1. So this is the same as 4 times 2 minus 2, 1. Now, why is this useful? See that 4? It comes out. Now, if it had been negative 4, it would come out as a positive 4. But the point is this is the same as 4 times the magnitude of 2 minus 2, 1. See, a scaling factor, which is what the 4 is, it scales it by that amount. So it's scaling that vector by length of 4. By a factor of 4. So you say, oh, well, great. Now I have a simpler problem in terms of what's going on here. So 2 squared, 4. Negative 2 squared, 4. 1 squared is 1. I say, oh, this is like 4 square root of 9. And probably it's a lot easier to say, oh, yeah, I know square root of 9 is 3, than to say, oh, yeah, square root of 144, gross. Math humor, right? Okay, all right, anyway, sorry. So 4 times 3 is 12. So, okay, so if you have a common scaling factor, pulling it out will make it a little bit easier to find the magnitude. Just remember to include that scaling factor. Now, is 12 our answer? And why not? Well, 12 is the magnitude. That would be if we were after a parallelogram, but we're not. We're after a triangle. So don't forget, you have to have a half. So our final answer is that the area is a half times 12, which is 6. Now, it turns out that's pretty simplified. And so life is good. Cool. Nice. Find a unit vector perpendicular to both 3, 2, negative 2 and 1, 2, negative 1. All right. Now, we are trying to make a perpendicular vector. And we say, okay, great. So in our mind, whenever we have the task that says make a perpendicular vector, and then what do? Well, we almost always say our gut reaction is, oh, that leads us to our cross product. So cross product is our go-to tool for making a vector which is perpendicular, especially if I say, oh, if I have two given vectors, the cross product is automatically 100% of the time, 100% of the time, automatically going to be perpendicular to both. All right, now with that in mind, we say, okay, cool. So we'd say, well, great, let's start. So 3, 2, negative 2, cross 1, 2, negative 1. And, all right, that's I, j, k. Put in the first vector, put in the second vector. And we do our cross product. And we do cross product with matrices, or at least I do, because I'm an old person who has a hard time remembering things, but I can remember cross products. Okay, so remember the diagonals. We're going downhill, right? I times 2 times minus 1. That would give us a minus 2i. J times minus 2 times 1 would be a minus 2j. K times 3 times 2 would give us a 6k. Now those are our downhills, but we've also got to do our uphills. All right, so here we go. 1 times 2 times k, that's 2k, but we subtract. Remember, you add your downs, subtract your ups. 2 times minus 2 times I, that's minus 4i, but we've got to subtract it. So we're going to subtract minus 4i. Minus 1 times 3 times j, that's minus 3j, but again, we're going to subtract it. All right, so let's see what we have. We have minus 2 minus minus 4, so that's plus 4. So that gives us a total of 2i. Then we have minus 2 minus minus 3, that's minus 2 plus 3, that's a 1j. Then we have 6 minus 2, and that would be a 4. 2, 1, 4. All right, now, what should we do? So here, I'm going to pause and just reminder. This point right here, you should say, okay, check. Now, how do you check? Well, you should always try to check your computations. So you could say, well, let me rerun the computations. But the easiest way to check is to say, I want this to be perpendicular to both. So we're going to do a quick dot product. Let's do this one first. 2 plus 2 minus 4, 0. Yes? Good. 6 plus 2 minus 8, 0. Good. So check, and what we do, we just check. Check by dot product with your initial vectors. And the point here is that this should be perpendicular to both. And it is. So this vector is perpendicular to both vectors. And so you're like, woohoo, we're done, right? Right? Come on, Steve, we're done, right? No, not quite. Not quite. What's our problem? There's one special word. We got to make sure we get every word accounted for. Unit. Unit means length 1. So we mean to make it a unit vector. Now you might say, great, does that mean that we have to restart from scratch? Actually, no. Whenever you have to find a unit vector of anything, you say, let's just find a vector that has the right direction, and then we'll fix it at the end. So when you have a unit vector involved, in some sense, the unit part is the last thing to do. So what we need to do is now to scale this down. So we say, okay, so we have the magnitude of this vector. We think it's bigger than 1. Well, it's got to be bigger than 1. Just the first entry is 2. So that's the square root of 4 plus 1 plus 16. And if you add those together, you get 21. So the square root of 21, also known as, that's right, the square root of 21. Yeah, it doesn't simplify. Not everything has to. So you say, all right, this vector, right direction, wrong length. This is its current length. So what do we do to get our right answer? Well, the thing is to scale by the reciprocal. So we divide 1 over the current magnitude of 2, 1, 4. And there we go. There's our answer. Right? Good. Good. And that is it. That is the correct answer. But you might say, you left a suspiciously big space there, Steve. Are you going to pontificate on that space, perhaps? I will pontificate. Yes, thank you. I appreciate you giving me this opportunity. is there another answer? Turns out, yes, there is one more answer that works. And it's actually pretty easy to spot. Can you see what the other answer would be? Well, what can I do to this vector that keeps its same length, is still in the same direction? See, I put quotes there. And so still works, right? Because the perpendicularness is a direction type question. Well, what can we do? The answer is multiply through by a minus. So essentially scaling by a negative is we're flipping the direction. So if it was going one way, now it's going the other way. So the other answer, and depending upon how people approach it, both are ways that you could get to it, would be 1 over root 21 minus 2 minus 1 minus 4. Now, do you need both answers? No. You just need one. Why? Because it says find a unit vector. It doesn't say find all of them. But I just want to point out that there are two possible answers here and how they're related to each other. All right, cool. Double the work, right? That's all right. It's good to go the extra mile. Suppose that u1 and u2 are orthogonal unit vectors. Okay, orthogonal means perpendicular. Unit vectors means they have length 1. C and D, non-zero scalars, so they're just normal numbers. If V is CU1 plus DU2, find U1 dot V and explain your answer. All right, so before we talk about what is V, let's actually dive a little bit into what this is telling us. This part right here. U1 and U2 are orthogonal unit vectors. So what does that mean? Well, what happens if you take the dot product of U1 with U2? Well, you get 0 because they're orthogonal. The dot product of orthogonal vectors, and orthogonal is another way of saying perpendicular, the dot product is 0. Okay. What about U1 dot U1? Well, that's the magnitude of U1 squared, and that's 1. Why? It's a unit vector. And U2 dot U2, that's the magnitude of U2 squared, which is also 1 because it's a unit vector. All right, so this first part right there becomes these statements. So that's probably going to be useful for us to know. And now we say, okay, so let's take U1 dot V. U1 dot V is equal to, well, it's U1 dot CU1 plus DU2. Okay, well, what can we do? We can distribute. So this is C U1 dot U1 plus D U1 dot U2. Okay, so justification is distribution. That's what we're doing here. Now, U1 dot U1 is 1 because it's a unit vector. So this is C times 1. And then U1 dot U2 is 0 because of orthogonality. And D times 0. So this right here follows from U1 dot U1 equals 1, U1 dot U2 equals 0. And again, we could just say unit and perpendicular. And then C times 1 plus D times 0 is C. Oh, say, can you see? So the answer is C. What's the explanation? It's this right here. So the explanation is actually this whole computation where we explained what tools we're using. And there you go. Yeah, that's the problem. That's the whole thing. This actually is hinting at some beautiful things which we will not really build much off of in this class, but there's this wonderful topic called linear algebra. It's a beautiful thing. And I hope that someday you'll get to see it a little bit more. And you'll say, oh, I remember all the good, happy times in our multivariable calculus class. We had these ideas. Now I see why. It's beautiful. It's beautiful. All right, nice. Find the projection of the vector minus 2i plus 2j plus 6k onto the vector I minus 8j plus 4k. All right, so it's a projection problem. Okay, so what do we do? Well, a good first step is to say, do we know the formula for projection? Say, well, yeah. So we have to be careful here. Now, one of the easy places to mess up a projection problem is to change the roles. In other words, which vector is the one that we're projecting onto? And now, in our case, we're projecting onto v. So we'll put the v down here, and we have our u. And the formula is, it's u dot v. So like take the dot product, v dot v times v. Now, I personally almost always go to component form. It's a weakness of mine. It's more along the lines of, I'm comfortable there, and I feel more confident that I'll make fewer mistakes. So I'm going to convert these vectors. So u, I'm going to write that as the minus 2, because that's attached to the I, the positive 2, that's attached to the j and the 6, whereas v, well, that's, I'm going to write that as a 1, because that's attached to the I, minus 8, and positive 4. All right, so let's go through and carry out the computation. So I'm writing down u dot v over, downstairs, v dot v, and then we're going to times it by v. All right, good, good. Now we do our work. Okay, so dot product, minus 2 times 1, negative 2. 2 times negative 8, minus 16. 6 times 4, positive 24. Downstairs. 1 times 1, 1. Minus 8 times minus 8, that's 64. 4 times 4, 16. And 1, negative 8, 4. Now, okay, we're doing good. We're almost there. Minus 2, minus 16 plus 24. That's 24 subtract 18. That leaves us with 6. Downstairs, 1 plus 64 plus 16. Well, that's 81. And then times 1, negative 8, 4. And we can do a little bit more. We say, okay, so notice that 6 and 81 have a common factor of 3. So we can pull that out and say, all right, that's 2 over 27, right? 2 times 3 is 6. 2 times 27, sorry, 2 times 3 is 6. 27 times 3 is 81. And we just have that. Now, this is an okay answer. However, they probably would like you to put it back into I, j, and k. So how do we write in terms of I, j, and k? Well, we'd say, okay, let's multiply through. So we have 2 over 27 times 1. That's in the first slot. So that would be 2 27ths I. Then we have 2 over 27 times minus 8. That's minus 16 over 27j. And then we have 2 over 27 times 4. And so that would be 8 over 27 times k. All right, so either one, either one. So there we go. The projection formula, right? If you know the formula, follow your nose. Make sure you know the formula. Make sure you know which vector goes where. And then just work it out. Not too much to this one. as long as you know what you're doing, you're probably okay. It's probably true in general, actually. Pro tip, know what you're doing. It's good. Strongly recommended. Let V be the vector 3, minus 2, 6. Find all unit vectors, U, such that U has the form 0AB, and the angle cosine theta is 2/7, and theta is the angle between U and V. All right. Cool. So, we have our work cut out for us. So let's think about what's going on here. Well, first off, we're told cosine theta is 2/7. Now, when you see cosine theta, you start saying, oh, I've seen cosine theta before, and in your mind you say, cosine theta, that's from a dot product. U dot V, that's magnitude of U, magnitude of V, cosine theta. You're like, cool. So now that I know I have this cosine theta here, then you say, okay, so what must be true? Well, what must be true is that we have the following. We have that U dot V, so that's 3 minus 2, 6, dotted with 0AB, has to be equal to the magnitude of 3, negative 2, 6, times the magnitude of 0AB times cosine theta. Now, let's clean this up. All right, on the left-hand side, what do we have? 3 times 0, 0. Minus 2 times A, minus 2A. 6 times B, 6B. Equals, here, well, the square root of 9 plus 4 plus 36. We'll come back to that. Magnitude of 0AB. Now that looks hard, but wait a second. What do we know about this vector? It's a unit vector. Oh! We're going to come back to this, by the way. We're not done with that. And then cosine theta is 2/7. Now, check this out. Check this out. 36 plus 4 is 40, plus 9 makes 49. Square root of 49 is 7. So it's 7 times 2/7, which is 2. So minus 2A plus 6B is 2. Or we get the following. Minus A plus 3B equals 1. Right? We just divide by 2. You're like, cool. But wait. We're not done. What's our issue here? Our issue is this gives a relationship between A and B, but it's one relationship. We need a second relationship. Okay, is there another dot product floating around? No. But there is something else. We come back. Remember, it's a unit vector. So we can say, oh, the magnitude of 0AB, in a particular magnitude squared, that better be 1 because it's a unit vector. Well, if you work it out, that's 0 squared, A squared, and B squared. So that's our second relationship. So now we're like, cool. We have 2 equations, 2 unknowns. However, it's not our usual 2 equations with 2 unknowns because one of them involves a square. So we don't be like, oh, we're going to combine things, add, subtract. No, we can't do that. So what can we do? Well, this is a prime candidate for substitution. So we're going to run through that. So we're thinking, okay, I want to substitute. And notice, can we solve for one of our variables in the first equation to substitute nicely into the second equation? And we say, well, boy, A is really tempting there because there's just a single A. So if you move things around, this will say that a is 3b minus 1. So now we're going to take that 3b minus 1 and we're going to plug that in. All right, so substitution, and again, we can't do elimination. I want to emphasize this. We can't do elimination because you have squares here, so you can't knock things out. But substitution works dandy. So we're going to put in the 3b minus 1 for a. So 3b minus 1 squared plus b squared needs to equal 1. So we square this out. We get 9b squared, then minus 6b, and then plus 1 plus b squared equals 1. Okay, now this is like perhaps making us ever so slightly nervous, but just slightly. Because notice the 1's cancel. That's nice. And so what do we have? Well, we really have 10b squared, because we have 9b squared plus b squared minus 6b equals 0. And if we wanted to, we could factor out a 10b. So why not? So you have 10 times b, and then b. Now, if you pull out a 10b from this term, okay, of course we got the b. We didn't get the minus. What's left? Well, it'll be 6 over 10. 6 over 10, also known as 3 over 5. And so we say, oh, okay, well, what does that tell us? Well, we need to have 10 times b minus 3/5 to be 0. And that leads us to our conclusion that, oh, hey, that gives us 2 possibilities. Well, it gives us 3 possibilities. 10 is 0, but turns out not true. B is 0. Okay, that could be true. Or we could get that b is 3/5. All right, great. And so now we say we're ready to give our answer. So it turns out there's 2 answers because we found 2 possible values. See how it says find all? Not just find one, but find all of the places where this is true. Okay, so how do we get our answers? Well, let's be a little bit careful here. We found b, but we also have to find a, but that's all right. A is 3b minus 1. So a would be 3 times 0 minus 1, which is minus 1. And that leads us to the vector 0, minus 1, 0, right? Because we have 0ab, 0ab. There's solution number 1. b equals 3/5. Okay, then what is a? Well, it's 3 times 3/5 minus 1. Now, 3 times 3/5 is 9/5. 9/5 subtract 1. Well, that's like 9/5 subtract 5/5. That leaves us with 4/5. So what's our vector? Well, it's again 0, a, 4/5, b, 3/5. And there's vector number 2. And so those are our answers, 0, minus 1, 0, and 0, 4/5, 3/5. You can check, they're both unit vectors, and they both satisfy this relationship, minus a plus 3b equals 1. And because that's all we needed, because that's what gives us our relationships. There we go. Life is good. So here we actually got a lot of mileage out of that unit vector. In general, when you're trying to solve for a problem that says, oh, find all the values a and b, or find all a or something, you're looking for relationships. Now, if you're looking for one value, you essentially are looking for one relationship. If you're looking for 2 values, like we were in this problem, you need to get 2 relationships. So that's why we said, oh, well, one relationship is coming from that dot product because of the cosine. Then we had to think about what's our second relationship. And that's when we came back and said, oh, yeah, there's a unit vector forces something about a and b. So look for relationships that you can use. All right. Fun problem. Nice. Woohoo! our happy dance. We got the answer, and it was nice. Ooh, 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 ah, 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 ah. A triangle in space has vertices u. So u here is a point, it's not a function. U is the point, and it's at 5, 4, 0. V is a point, and it's a. Okay. And W is a point 7, 4, 4. A is an unknown constant. Oh, well, we better do something about that. We better solve for A. Well, it says determine all values of A such that the triangle UVW has area 6. Okay, all right. Interesting. So let's sketch what we have. So we put our 3 points. And again, we don't have to stress too much about getting the points exactly right. So we say, okay, we'll have our first point, U, which is at 5, 4, 0. Our second point, V, which is at A, and our third point, W, which is at 7, 4, 4. So for now, the key is understanding, not precision. If you have to choose between understanding and precision, start with understanding. Precision can come if needed. All right, so we have our lovely triangle. Now notice the triangle will vary. So as you change A, you change which triangle you have. And of course, as you change your triangle, you're changing the area that it has. And so it's sort of like, where's that sweet spot for A? Now, we have a big hint. We're told, we see a word, area, and we also see the word triangle, and we're like, hey, I know something. There's a tool we have that is very useful for computing areas of triangles in 3D space, and that's cross product. So we say, oh, okay, so in particular, if you recall, we have U and a vector V. If you take U cross V, that's going to be this area. So the area of this parallelogram is U cross V. So if I want the triangle, which is half the parallelogram, what do we do? Well, we take half of the area. So it's half of the magnitude of the cross product. So, okay, so that's good to know. All right, so we sort of have the punchline. We're going to find two vectors, and then once we find those vectors, we're going to take the half that cross product, and that's our area. All right, so let's figure things out. Step one, let's talk about our vectors. Now, we have vectors, so we just pick a vector. Now, I have no reason to go against the order they gave us, and so I just say, well, let's anchor. We choose our anchor. We'll choose U. So we're going to have two vectors, U over to V, U over to W. Now, to find U to V, we say, well, what's the change? And we take differences. So we went from 5 to A. So the difference in the first entry is A minus 5, right? End minus beginning. Second entry, A minus 4, and beginning. Third entry, A. All right. How about here? Well, again, we're talking differences. We went 5 to 7. That's a difference of 2. 4 to 4. That's a difference of 0. 0 to 4. That's a difference of 4. All right, so those are our two vectors for our two sides. You've got to make sure you find those vectors. Don't use the points. Points aren't vectors. You can't take cross product of points. You can take cross product of vectors. So we now have the following. The area of this triangle is going to be 1/2 the magnitude of our U cross V. So these are our two vectors. We'll do A minus 5, A minus 4A, cross 2, 0, 4. Now, before we get too far along, that equals 6. I'm going to do two things. Let's multiply across. So we say, aha, using our advanced paper technology, I can multiply both sides by 2, so that this becomes 12. See how fancy that was? And then I can square both sides. All right, so what we really need to do is we need to solve the following. So we need to solve, when does the magnitude of a minus 5, a minus 4a cross 204 squared equals 144. Okay, so we're gonna, this is our equation to solve. So let's go and do this cross product. We're gonna need to do it. And you might say, well, wait, how can we do it? We have a's. How can we, if we don't know a, how can we take the cross product? And the thing is, a is an unknown, but that's okay. We're allowed to use unknowns in cross products. Cross products are very resilient. And it'll be like, you don't know it? That's cool. Just write it as the unknown. Solve for it when you can. And if you like, go ahead and send me a letter and say, hey, cross product, I found that unknown I was looking for. And cross product will be like, I knew you could do it. I believed in you. You're awesome. Because you are awesome. All right, now here we go. So cross product, I, j, k, and a minus 5, a minus 4, a, and 2, 0, 4. I have to be careful because my a's sometimes start to look like my 9s. So this is a pro tip. Learn to read your own handwriting. And if you're worried, be extra careful and exaggerate if you need to. All right, so I'm just going to talk through it. I'm not going to mark the diagonals here because hopefully we've gotten good at that. So we have I times a minus 4 times 4. So that's 4a minus 4i. J times a times 2. 2aj. K times a minus 5 times 0. 0k. That's good. All right, now going the other direction. 2a minus 4k. So subtract 2 times a minus 4 times k. All right. 0 times a times I. Well, that's 0. Because it's hard to recover from 0. So subtract 0i. Notice I didn't add 0i. I subtracted 0i. Why do I point this out? Because it's me being silly. But remember, it is subtraction. Okay, 4a minus 5j, but we, of course, are subtracting 4a minus 5j. All right, which would give us here, well, in our first slot, we'd have 4a subtract 16. And then we subtract 0. So 4a minus 16. Here we have 2a minus 4a and a plus 20. Well, let's say we put the plus 20 here, and 2a subtract 4a, that's minus 2a. Okay? And then 0 minus 2a and plus 8. So I'll write that as 8 minus 2a. All right. Good. Good. Now, you might be getting a little nervous. That's all right. Don't panic. We'll get there. We're following the steps. And you might say, well, what if it gets messy? Sometimes in the process of simplifying things, it gets a little messy in between our endpoints. But know that you're doing the process right and have faith. When in doubt, double check your logic, double check your work. But sometimes the middle steps will be a bit messy. All right, now here we go. So we have that 144. This number is equal to the magnitude of the cross product squared. So that's equal to the magnitude of 4a minus 16, comma, 20 minus 2a, comma, 8 minus 2a squared. Okay, well, that's 4a minus 16 quantity squared, plus 20 minus 2a squared, plus 8 minus 2a squared. Okay, catch your breath, strap in, it's going to be a wonderful ride. 4a squared is 16a squared. All right. Now, 4a times minus 16, well, that would be minus 64. But I'm going to do it twice, right? Because you have the two cross terms. So 4a times 16 times 2. And that will give us a grand total of 128. So minus 128a. 16 squared is 256. Then we come to the next term, 20 squared. That's 400. And 20 times 2a is 40a, but we double that. So it's going to be subtract 80a and plus 4a squared. And then we have 64. And then it's minus 32a because we have two, first term times second term. Okay, so that's minus 32a. And then plus 4a squared. All right. Now, let's do our gathering. So I'm going to gather here. We have our a squares. We have 16a squared, a 4a squared, and a 4a squared. That's 24a squared. Okay. We have minus 128a, minus 80a, minus 32a. All right. Well, what would that be? Minus 208 from those terms, right? Yeah, it is. Because 128 plus 80 is 208. And then add another 32, that would be 240. So it's minus 240a. Okay? 128 and 80 and 32. 128 plus 32, for instance, is 160, plus 80 is 240. Oh, that's kind of nice. Huh. It's almost like they planned for something to happen. Could they have done that? I hope. All right, well, let's see what else we have. We have 256 plus 64. What is that going to turn out to be? That'll turn out to be 320. Plus 400 is 720. And then we have minus 144. So actually, let's be careful here. So like we said, 256 plus 64, 320 plus 400 is 720. And subtract 144. And, it's okay to be like, how do you do math? And math sometimes is interesting. So this should be 576. Okay, well, if that's what it says it is, then that's what it is. And that equals 0. All right. Now, what would be great? Well, you see how that has a factor of 24? That has a factor of 24. Is 576 divisible by 24? Have they been kind to us? Because right now, it doesn't feel like they've been kind to us. Well, let's try to divide. All right. It's been a while. Boy, this brings me back. Okay, so 24, well, can't divide into 5. So 57, 48 is just below 57, relatively speaking. So that's 2. And then we subtract 48. And 57 subtract 48 would be 9. And let's see, does 24 go into 96? It does. It's 24. And we're like, 576. Oh, yes, of course. That's 24 times 24. We all knew that, right? You knew that, right? Sure. Okay, great. Okay. Ho, ha, ha. Those math gods are smiling at us. Our lovely, kind professors. They really are lovely, kind people. Okay, so let's clean this up because everything has a factor of 24. Right? Even, that's 24 times 10. So divide out by 24, and we get to the conclusion that we need a squared minus 10 plus 10. I can do this. A squared minus 10a plus 24. There we go. Equals 0. I forgot my a for the 10. All right. Well, cool. So Now, this looks reasonable. Like I said, it might get messy, but your teachers love you. I know they do. They're good people. They have big hearts, but not in the bad medical way, like in the good caring way. They care about you. So if things are getting really bad, check your work. But don't be afraid to be like, you know what? I believe in them. I believe in my professors. Okay, so what are we looking for? Two numbers that multiply together give 24, but would add together to give 10. Well, 24 is like 4 times 6, and that adds, oh, nice. So this looks like a minus 4 times a minus 6, I think. Let's check. A squared, that's good. Minus 6a minus 4a, that is minus 10a and plus 24. And, okay, so that gives us two possibilities, because a could be 4 or a could be 6, right? Because once you have things multiplied together to get 0, one of them had to be 0. So our final answer, all possibilities, are 4 or 6. And that's it. We're done. We made it. We made it. Now, I'm going to put a little aside note here. When I write these problems, these are variations of problems that you might see. Sometimes my variations are going to be slightly more challenging. And so I don't want you to be like, oh my gosh, am I going to have to do things this bad? I don't think you will. I really don't. But I want you to understand the process. So understand the process. If you just walk in at this moment and say like, oh my gosh, I see so much, like, I can never do this. But think about the process. Think about the steps. Oftentimes, you just have to say, look, I don't have to solve the whole problem. One step. If I can do one step, I can make progress. And then I'll follow that first step by a second step. And if you do enough steps, you get to the end. So what were the ideas? We knew we were after area of triangle, so we said cross product. We figured out what were vectors for two sides of the triangle coming out from one vertex. We said, okay, the cross product times a half equals the desired area. We did the square. Now, the reason we did the square is because magnitude has a square root. We don't like square roots. We avoid them when we can. So we have a relationship about the square of the magnitude of the cross product. So we ran the cross product with our a's, and then we followed through what that magnitude equation gave, and that gives us our answer. All these are things I know you can do. I believe in you. You can do this. You're great! So, find the value of a and b if this vector 1, 4, 7 is a normal vector to the plane containing the points 3, 5, 4, a2, b2, 7, 3. Okay, all right. Now, we're going to have a long discussion on this one. So let's start by saying, what do we mean by normal vector to the plane? And the punchline here is when you see normal vector to the plane means you're perpendicular to the plane. And in particular, you're perpendicular to all vectors in the plane. So that's the key here. You say, all right, cool. So I know that this particular vector, 1, 4, 7, is perpendicular to any vector that's in this plane. And I know 3 points which are in this plane. And that's sort of our great aha. Now, I want to talk about 2 ways to do this problem. One way is the way that they intended you to do this problem. The other way is the way that you'd actually do this problem. And we're going to have a discussion. Okay. All right, so here's how they intended you to do this problem. All right. They said, oh, I bet you students will think of the following. So there you're going to say, oh, I know how our students think. And of course, we have pretty good idea of how students think because, you know, we taught you. So we're like, well, they're going to write down these 3 points, 3, 5, 4, A, 2, B, 2, 7, 3. And then they're going to say all these are points in our plane. So we have this plane, it's this sort of vaguely defined plane that has all 3 of these points. And we say, all right, I am going to think about this as I'm going to create something which is perpendicular. So idea, create a perpendicular thing. Okay, so now if you want to create a perpendicular thing, what do you do to create something? Well, the creation is cross product. So this approach is going to say, let's use a cross product. Okay, so now I say, well, I have to be perpendicular to 2 things in the plane. What are 2 things in the plane? And, well, I have points. Now, points are not vectors. I said this several times on several problems, so I'm going to keep saying it because it's really important to remember. Points are not vectors. Vectors are vectors and points are points. But you can go from pairs of points and create vectors. And so the aha is like, hey, let's make vectors in the plane. So I'll go from P to Q and from P to R. And now I say, well, what's the change? Well, from P to Q, I went from 3, I got to A, so it's A minus 3, you know, N minus start. 5 to 2, down by 3, so subtract 3. 4 to B, B minus 4. How about here? Well, P to R, well, I went 3, subtract 2, minus 1, 5, subtract 7, minus 2, and, oh wait, sorry, plus 2, right? Because I went up by 2, so 7 subtract 5, excuse me. And then 4 to 3, 3 subtract 4 is minus 1. Okay, so our vectors in the plane are the vectors A minus 3, B minus 4, and minus 1, 2, minus 1. All right, so here we have 2 vectors in the plane. Now, why do we need 2 vectors? Well, we need to take a cross product of them. So we have to pick 2 vectors which are perpendicular to each other. So we say, okay, starting with our 2 vectors, and this is not a bad time to pause and just double check to make sure, like, okay, are these vectors correct? Because if your vectors are wrong, everything else that follows will have wrong computations. You know, right ideas, wrong computations, we'd lose points. We don't want to lose points. We love our points. We want all the points. All right, so we're going to take the cross product, say that's our normal thing. Well, hey, we have our normal thing, and so we're going to set that to our normal thing. And then we're going to figure out what that tells us about A and B. Okay, so that's our idea. All right, well, here we go. Here we go. So we have to do this cross product, I, J, K, and I didn't give myself a lot of room, but A minus 3, B minus 4, minus 1, 2, minus 1. Okay, so down the diagonals, I times minus 3 times minus 1, 3i. J times B minus 4 times minus 1, well, that's going to be minus B minus 4j. K times A minus 3 times 2, well, that's going to be plus 2 times A minus 3 times K. All right, so we go down our diagonals. Now we got to go up our diagonals, and remember, we subtract. Minus 1 minus 3K, that would be a plus 3K. 2, B minus 4I. Oh, wait, I said plus 3K. Oh, classic mistake, Steve. We go up, right? Minus times minus is a plus, but we are subtracting that. Okay, so double check, double check. Okay, 2 times b minus 4 times I, so we're going to subtract 2 times b minus 4I. And then here, minus 1 times a minus 3 times j, so we're going to subtract. But we have a subtraction there. Minus and minus does make a plus, a minus 3 times j. So that gives us, here in the I slot, well, we have minus 2b, and then a plus 8 and a 3. And, well, okay, 8 plus 3 makes 11 minus 2b. And then here in this slot, well, let's see, we have a 4 minus 3 makes a 1, a plus an a, and minus a b. And then here, well, we have 2a and minus 6 minus 3, so that looks like 2a minus 9. Now remember, what do we want this to be equal to? 1, 4, 7. All right. Well, we compare. We say, oh, hey, that better line up. So 11 minus 2b better be equal to 1, right? So that says 2b has to equal 10, or that tells us that b has to be 5. And then we say, oh, what about this last slot? Well, we get 2a minus 9 has to equal 7, or 2a has to equal 16. So what is a? A has to equal 8. And now you might say, well, wait, what about this middle slot? And you say, oh, yeah, what about that middle slot? Well, you'll plug it in and you'll find out 1 plus 8 is 9, and 9 minus 5 is 4, and so it'll work. In fact, it has to work. If it doesn't work, mistakes were made. And so we say, oh, well, this is great. So our answer should be a equals 8 and b equals 5. And it's like, okay, we found the answer. Life is good. Woohoo, we're done. Okay. This is how they intended you to do the problem. Now we're going to talk about what's going on, what they didn't intend you to do, and why this is correct, but misleading. Okay, so here's the thing. I just want to preface this by saying I am not trying to criticize the problem writers. I know what they intended, and it's just their subtleties. We love our problem writers. They're great people. There's a couple of things to note. Do you see this word, That's a very important word. Normal vectors are not unique. There are many normal vectors. And so I don't have to pick 1, 4, 7. I could have picked 2, 8, 14, for example, or 3, 12, 21. I can scale this by any number and it's still normal, because the only thing that matters is the direction, not the magnitude. Okay, so why is that important? Well, you see, our calculation used that it was this particular vector. So when we say find the value of a and b if 1, 4, 7 is a normal vector to the plane, well, that's misleading, because I could have picked other normal vectors and that would have led to other values of a and b. So what's another way we could have approached this problem? And what would it have given us? Okay, so another way to approach this problem is say, okay, let's think about our different tools. We have a perpendicular thing. It's perpendicular to all vectors in the plane. So here's idea number 2, which is we're going to say, hey, instead of create a perpendicular thing, let's test a perpendicular thing. Now you might say, well, what do you mean by test? Well, how do you test something is perpendicular? Well, the answer is the dot product. And so the dot product will give us a different way to think about this. So we say, hey, you know what? We know that this vector, a minus 3, comma, negative 3, comma, b minus 4 is in the plane. We know that this vector is perpendicular to anything in the plane. So we know that this dot product has to be 0. Has to be. Because anything in the plane is perpendicular to this normal vector. Because the only thing that determines perpendicularness is direction, not size or magnitude. All right, so what does that lead us to? Well, it leads us to a minus 3 times 1 minus 12 plus 7 times b minus 4 has to equal 0. Or, if you move things around, that says a plus 7b. And let's see, we have minus 3, minus 12, minus 28. We're going to move all that to the other side. 12 and 28 together would be, well, 12 plus 28 is 40. Plus 3 makes 43. Now, what's the answer? Literally, anything that satisfies this. So any a and b that satisfies this relationship satisfies the question. So there's not one answer, there's infinitely many answers. And so that's why this is sort of a kind of a question. And because for any a and b where this is true, it's in the plane. Now, what about our a and b? Well, let's check it out. A is 8, so 8 plus 7 times 5, 8 plus 35 is 43. So this indeed is a point in the plane, and it leads to a point in the plane. But it's not the only thing that works. So there are actually infinitely many correct answers in the way that this problem was stated. The thing is that they had meant to ask a different problem, but they added this extra layer. They had meant to say, hey, we want to have that the cross product of these two vectors is the vector 1, 4, 7. If you state the problem like that, then the way we did it in the first iteration is correct. However, if you're asking the problem in this format, where you add this extra layer, it's like, oh, well, this is a normal vector to a plane. It turns out that there are infinitely many correct values for a and b. And again, any a and b that satisfies this is a point that is in that plane. All right. So that's my aside. I hope this was somewhat enlightening. I promise that as we get more into planes, this discussion will make a lot more sense. But I just wanted to give some context for this problem. All right. Good. Good. Let's do some more. Find a unit vector perpendicular to the plane PQR, determined by the points 5, 1, negative 3, 7, 4, 1, 6, 2, 1. Okay, so let's see what we have here. So we have a plane. So let's draw our plane. All right, so let's imagine this is our plane. And we have some points P, 5, 1, negative 3, Q, 7, 4, 1, and R, 6, 2, 1. Okay, so we have our plane, and we have our 3 points that are in the plane, and it turns out that 3 points will in fact determine a plane. Now we want to find a vector which is perpendicular to this plane. We say, okay, so we need to make a perpendicular thing. We need to say, we know how to make perpendicular things. So whenever you see perpendicular, you always have to ask the question, are we making a perpendicular thing, or are we testing, or if you like, verifying a perpendicular thing? And here we're making one because we have to find one. So to make a perpendicular, we're going to use the cross product. So make perpendicular, that leads us to cross product. All right, that's our side note, our game plan, if you will. So okay, so now we say we know we're after cross product. Now, if we do cross product, what do we need? We need some points so we can take the cross product up. Sorry, not some points, some vectors. Haha, gotta catch myself. All right, some vectors. Now, these are not vectors, these are points. But we can create vectors from the point. So we pick a point. It doesn't matter which point we pick, and but the point can be any one of them. I'll pick P. If you want, try this with Q and R. You'll see that you'll get the right answer in the end. All right, so we're going to go say P to Q and P to R. So we can write PQ, and that would be written as PQ with an arrow. So that's the vector starting at P going to Q. And now we say, hey, let's look at the change. 5 went to 7. That's a change of 2. 1 went to 4. That's a change of 3. Minus 3 went to 1. That's a change of 4. 2, 3, 4. Well, that's a nice number. How about P to R? All right. 5 went to 6. Change of 1. 1 went to 2. That's a change of 1. Minus 3 went to 1. That's a change of 4. 1, 1, 4. All right. So we now have two vectors in the plane. So these are directions in the plane. So if we were to take the cross product of them, there'd be a new vector, and that new vector would be perpendicular to the first vector, perpendicular to the second vector. So it would have to be perpendicular to the whole plane. That's our great aha. So we say, okay, plan. Let's find this cross product, PQ cross PR. And all right, I, J, K, 2, 3, 4, 1, 1, 4. All right, well, diagonals, right? So let's go through our diagonals. We have I times 3 times 4, 12I. J times 4, wrap around, times 1, 4J. K times 2 times 1, 2K. Now, in the other direction, what do we have going on? 1 times 3 times K. Okay, that's 3K, but we're going up, so we subtract. 1 times 4 times I, that's 4I. We're going up, so we subtract. 4 times 2 times J, that's 8J. We subtract. That leads us to the vector. 12 minus 4, well, that's 8. 4 minus 8, negative 4. And then 2 minus 3, negative 1. All right. Now, quickly, you should check. How do you check? To test perpendicular, use the dot product, and test by taking the dot product to what you started with. 16 minus 12 minus 4, 0. 8 minus 4 minus 4, 0. Nice. All right, so this is not our answer, but it's a good answer. This has the right direction. It's perpendicular to both of the original vectors, which means it's perpendicular to the plane. Why is it not the right answer? Well, it has the right direction. What does it not have? It has the wrong length. It's not a unit vector. Okay, so let's find the magnitude. So the magnitude of 8, negative 4, negative 1, well, that's the square root of 64 plus 16 plus 1, which is the square root of 81. Oh, they give us nice numbers. That's 9. All right, nice. Okay, so now, right direction, wrong size. It's too long. This has length 9, has to have length 1. So how do we get the right vector? Well, now you scale by the reciprocal of the magnitude. So you'd have 1/9 of 8, negative 4, negative 1. Or, if you prefer, you can move it in. You can say, oh, that's like 8/9, negative 4/9, negative 1/9. And that is right direction, right length, and life is good. Okay, are we done? I don't want it to end. Can we maybe get another answer? Well, yeah, we actually can in this case, because it turns out there are actually two right directions. So when I say right direction, it's correct. But the thing is, we can have sort of, if this is our plane, we can have a vector coming out the top or a vector coming out the middle. Sorry, out the bottom. So from either the top or the bottom. So in other words, there's this other vector pointing in the opposite direction, which again is still perpendicular to both of the vectors we started with. How does it relate? It's the negation. And so the other answer is we could have done 1/9 -8 +4 +1, or that could become -8/9 +4/9 +1/9. So that's also a correct answer. Now, the good news is you only need one of these four. Any one of these four is correct. There are all different ways to write it. You could even write using IJK notation if you prefer IJK notation. Great, that's wonderful too. But there we go. A wonderful way to finish up this session. Thank you. We made it. We did it. Woohoo! Yeah. All right.